Hello and welcome. My name is Christine Perret and I'm the chair of the Area Research Committee. And I am the host of today's webinar on the subject of distributed mobile augmented reality architectures in the lab, meaning in research, and beyond, as perhaps you will be seeing them in your enterprise and industrial environments in the future. I'm very happy to welcome you for today's webinar. The way we will be doing this is we will have the prepared remarks first. If you have questions during our presentations that you'd like to ask, look for the questions panel in the GoToWebinar control panel. You can type your question in there and I'll be happy to either answer those questions myself if I know the answer, or I'll bring them to Maria at the end of this her prepared remarks. First, I'm going to present a short overview about the AR for Enterprise Alliance. Then I'll have the pleasure of welcoming our guest speaker today, and she will introduce herself further. And as I said, we can then take questions from you. And between, during the webinar, as you are in listen-only mode, you can also, I believe, you can raise your hand and we will be able to interact after the prepared remarks. So the AR for Enterprise Alliance is an industry association whose mission is to accelerate the development of the enterprise AR ecosystem. What do we mean by the enterprise AR ecosystem? Well, it starts really with the top of this small pyramid, the enterprises, typically large enterprises that are seeking to apply and introduce and adopt augmented reality where they can save money, save time, reduce errors, or reduce risk. In other words, where the investment that they make in digital transformation and in other automated systems can be seen and interacted with by a human being. Augmented reality has its place where there are people in the workplace and where they need to interact with data and machines or other people. Supporting the enterprises that are adopting augmented reality are two groups: the providers of technologies, and of course they develop a wide variety of components or integrated solutions or services that are tailored to meet the requirements of the enterprises, either in terms of their performance or their security or some other requirement of the enterprise IT. And then also supporting the enterprises and the providers are the non-commercial entities. And these are a wide variety of universities and other types of institutions, research or government agencies who are supporting the development of the new frontiers, the pushing the boundaries of this technology as we go forward. And so these are the three segments that we think of when we speak of an integrated or comprehensive ecosystem. And the area supports that ecosystem in four ways. We produce and we curate thought leadership content, and we provide it on our website through social media, also in webinars like this one. We also have fireside chats and podcasts and other forms of content to help people understand the benefits of augmented reality, the return on investment that they can expect, and the how to overcome challenges. We also support the ecosystem to find each other, for providers to find enterprises and to partner with other providers in many cases, to help the large enterprises find qualified providers of solutions and services, and for these different groups to share their value and their insights to reduce the barriers. We also know that there's a tremendous gap, there's a shortage of people who are skilled and who are trained and certified to work in enterprises on the subject of augmented reality, either to deploy augmented reality, to build experiences, design experiences, human factors, and these subjects are all part of the many skills that are needed for our industry to be successful. And we are trying to help close that skill gap by promoting education programs and job openings for people who are trained. And finally, we approach the different barriers to adoption through our committees and our variety of different committees that are working in a more focused way, such as working on safety or security and requirements to be able to develop new thought leadership content or best practices. And so these are some of the ways that we are supporting this ecosystem. And with that, I'd like to now introduce our guest speaker for today. Actually, I'd like to have her introduce herself. Maria Gorlatova is a professor at Duke University. And Maria, I've just made you presenter, so thank you. Perfect, I see your screen.
Thank you, Christine. Let me just bring it full screen.
Perfect.
You see
That's
the
right.
screen, the screen and no notes, right? Okay, excellent.
That's perfect. Yes, thank you.
Okay, excellent. Thanks so much, Christine. Thanks for having me. I'm absolutely delighted to be here to talk about our work. So we work on next generation mobile augmented reality architectures where augmented reality devices are supported by external infrastructures, by external sensors, and by edge computing capabilities that we can use to offload some of the processing off of the AR devices to improve the capabilities of integrated AR systems. As I'm an assistant professor at Duke University. I work in both ECE and CS departments. And before joining Duke, I did a postdoctoral fellow position at Princeton and did my PhD at Columbia. And I've also had the pleasure of working for several companies along the years. Some of the companies are shown on the screen here. At Duke, I lead the Intelligent Interactive IoT Lab, where our goal is to create infrastructures that enable augmented reality to be reliable and context aware. And when I talk about reliable augmented reality, I mean augmented reality that you would truly trust your life to, that you would trust to have as a part of a medical procedure that's done on you, or you would trust to guide you in working with a large and potentially dangerous robot, for instance. And when we talk about context-aware augmented reality, we talk about adapting AR experiences to the state of the environment and the state of the user, using AR to identify objects in the space around you, using AR to map the environment around you, and developing the types of augmentations that respond to the state of the user, that are different for a user who is tired, for instance, or who is engaged, different for an expert and different for a novice in a task. So our work is generously supported by several federal agencies as well as several companies. And in today's talk, I'll describe the architectures we envision for next generation augmented reality. I'll talk about how they enable improvements in spatial and semantic awareness, the awareness of the state of the environment. And I'll also talk about how they enable taking user context awareness to the next level, having us get more information about the state of the environment and the state of the user, and have this information be more reliable. So overall, existing mobile AR architectures are already absolutely stunning. The graphics that you get on modern AR systems and the ability to truly place AR content in context of the real world are already just absolutely mind-blowing. But the modern standalone mobile AI architectures have a lot of limitations. So fundamentally, these are mobile architectures that do not have the computational capabilities of standard plugged-in hardware, such as servers. And fundamentally, on the sensing side, they are limited as well. So while AR systems do have a multitude of sensors, they are placed in only one location in the environment at a given time. And as the user moves, the sensors move with him or her. So we are only getting one fairly narrow take on the world for an AR device at any given point. And this is where we are imagining using additional infrastructures to augment what the augmented reality devices are capturing these days. We can use IoT to get additional data about the state of the environment and potentially even control the state of the environment to get to the best possible augmented reality experience. And we are planning to use wearables to get additional information about the state of the user as well. And all of this is helped with the so-called edge computing. And this is where advanced computing capabilities are moved closer to the end users. And I want to talk a little bit about edge computing, that it is envisioned to stand in complement to cloud computing, where cloud computing is quite centralized. On the screen here, you see a set of cloud computing data centers that are made available by one of the big cloud providers, that's AWS. And the maps for the other cloud providers look quite similar. So you see that literally on any given continent, there are a handful of such data centers, which means for many locations to be able to access the data center, the data has to travel hundreds or even thousands of miles away. And this has been working well for the types of use cases that have been envisioned for cloud computing. But with new applications such as augmented reality, smart cars, virtual reality, and drones, we are starting to run into fundamental limitations of these approaches. That fundamentally the signals have to travel hundreds or thousands of miles. And the latency that we get as a result of that just isn't good enough for emerging applications. And these applications are also producing lots and lots of data. So having to push this data these distances just doesn't work for these emerging applications. And this is where we come to edge computing, where we imagine taking the same computing capabilities, but moving them closer to the end users. And several different versions of edge computing exist. You can imagine moving this computing capability on-site within your building, or having it co-located with your local mobile base station, or having several computing servers placed somewhere in your region. In all of these cases, I want to note that we do not just talk about content placement. So these are not content delivery boxes. And we do not just talk about forwarding information. We talk about actually doing some execution on behalf of mobile devices to enable them to run complex algorithms at low latency. And edge computing is generating enormous interest these days. There are cloud provider services that use edge. There are services that are made available by wireless providers. So overall, there's a set of there's enormous excitement and interest and realization of the potential of these architectures. And augmented reality is one of the prime use cases for them, since augmented reality requires so much processing to be done on such low latencies. So this is how we imagine putting it all together. We have AR devices and other devices that help sense the world around the user and sense the state of the user, him or herself. And then these devices are transmitting the information to the edge server that is helping process this data in the best possible way to help AR devices reach a better state of understanding of the world and the user. And here we talk about using edge computing for helping with simultaneous localization mapping, for helping with scene understanding, such as identifying dangerous objects in the environment, for having edge computing run advanced context-aware algorithms that provide a high degree of environmental awareness, user awareness, and perhaps even social context awareness. And all of this information that is calculated on the edge server would then be transmitted back to the AR device to change the augmentations that are shown for the user, to have the augmentations adapt to the state of the environment and the state of the user at the same time. And I want to mention the limitations in this area for existing mobile AR devices. As I mentioned, and I'm sure as you have seen, augmented reality is already truly impressive in its ability to merge physical and digital worlds. So the graphics that we are already generating and our ability to place graphics on real surfaces, for instance, that's already amazing. And my very favorite application to work on is to use augmented reality for surgery. This is shown on the screen to the right here, where we take a preoperative scan of the patient, we take a CT scan, we convert it to a hologram, and we place that hologram directly on the surgeon's view of the patient. This allows the surgeon to directly target the exact part of patient's anatomy that they would like to get to without having to look away and without having to do mental reprojections. So this capability of augmented reality is just absolutely incredible already. But augmented reality has a lot of limitations as well. For instance, unless you are using markers, or unless you're creating highly specialized setups, such as the one that we're creating for our AR-assisted surgery project, augmented reality still isn't perfect in enabling the understanding of the topology of the world around us. So it's making a lot of errors in spatial awareness, and I'll give you some examples in the next couple of slides. It is also quite limited in its ability to understand what the user is doing and what the user is thinking. We can say something about the user. There are some experimental deployments that go towards that direction, but we can definitely do much more in that aspect. And finally, AR's ability to understand the semantics of the world around it, the nature of objects and surfaces in the space, is also quite limited as well. There are some existing prototypes and deployments, and there are limited limited capabilities available. But again, we can definitely do much more with the data that AR devices are capturing. So I wanted to give you some examples of errors in spatial awareness that I've mentioned. And some of them are on the screen here. Basically, errors in spatial awareness result from an incorrect understanding of either the mapping of the world around the user or an incorrect understanding of where the AR device is positioned with regard to that mapping. And this leads to holograms not being placed correctly. So they could be shifting around, and that's called drift, the unintended motion of holograms. They could be produced at an incorrect scale, or they could be showing up differently for different users if different devices have a different set of understanding of the world. So the examples that are shown on the screen here correspond to very commonly encountered conditions. On the left of the screen, you see an example of drift, where we've placed this virtual lamp in one location on the table. And then over time, as devices' understanding of its location with respect to the real world has been changing, the lamp ends up shifting to the other part of the table, or ends up sliding off the table entirely. So this this level of drift would clearly interfere with the usefulness of augmented reality application. And to the right of the screen, you see an example of holograms that are incorrectly scaled. So in the example on the left, the chair is supposed to be the size of the other chair, but ends up being gigantic. And in the example on the right, the echo show that's generated ends up being absolutely tiny. And this has to do with the correct understanding of the depth of the surface in comparison to the AR device. That if we misjudge the distance between where we want to place the hologram and where we are, then we end up generating holograms that are of a completely wrong size, as you see here. So we've quantified these artifacts over several recent lines of work. I'm happy to give you some data on these if you're interested. I just wanted to show you an example of what we quantified for drift, that we looked very closely at the level of drift that is encountered on modern platforms, headsets, as well as mobile phones under different conditions, in different environments, and for different user actions. And our results are shown on this graph here, where the y-axis is a logarithmic scale drift value encountered for different actions. And this is a busy graph. It shows the drift values that are captured for several platforms that are shown on the screen here. And you can see that for many of the settings that we consider, the drift is very, very significant, that we have holograms that shift around by 10 or 15 or more centimeters on average under many cases. So while there are some platforms that are good, that only result in drift of around 2 centimeters on average, for many, this core ability of reliably placing content in context of the real world and having it stay there just isn't available still, despite all the advances that have been made in the area of mobile AR. So overall, while the capabilities are stunning, there is a lot of work to be done to make it reliable for sure. So I'll talk about our work on using multi-device architectures for improving spatial and semantic awareness for augmented reality, improving the understanding of the topology of the real world and the nature of the contents in it. And this is where we can use IoT devices to get additional vantage points that can help us do better in estimating the state of the world. So we can have additional captures that help us run SLAM algorithms and additional captures that help us identify objects in the environment, as I'll describe briefly. IoT can also provide persistence observability, so that, for instance, we install an IoT-based camera in a space and have it monitor the space in between AR sessions. Then we can see if the space has changed between the sessions and if the AR device needs to remap the scene, or it can forego remapping and achieve reliable tracking without it. And with IoT, we are also able to control the environment as well. So for instance, we can imagine turning on the lights to improve the performance of AR devices as appropriate. The other area where supporting infrastructures can really help, this is the area of using edge computing to run more advanced computational algorithms. And this is, I would say that a lot of work on IoT supporting of AR is more futuristic, but a lot of work on edge computing supporting for AR is closer to being ready for deployment. And multiple elements of it are being explored by multiple groups. So for instance, there's very interesting work on using edge computing to run advanced light estimation algorithms to improve the photometric registration of virtual content, to improve how well a hologram blends with the real world. There's very interesting work on using edge computing to run computationally expensive parts of SLAM pipelines for AR devices. This allows to shift a lot of resources of mobile devices to the supporting infrastructure and can potentially enable significant savings in battery usage and lead to the improvements of lifetime for AR devices. And then finally, there's also interesting work on using edge computing to improve semantic awareness, awareness of the state of objects and surfaces in the environment. So I'll talk about our work in this space. Basically, in many cases of AR usage, it would be very helpful to know what the objects are around the user. So for instance, you would want to detect if an object is hazardous or if there is an object configuration that isn't right, or you want to see that the space is lacking a certain object that you would expect to be there. Overall, being able to automatically detect what's happening around the user, what objects and surfaces are there, has the potential of enabling many applications of AR that are very helpful. And usually these types of inferences about the state of the real world are made with deep neural networks. But the issue is that DNNs aren't generally reliable in the real world. They make a lot of mistakes. They make mistakes if the device captures are damaged in any way. So for instance, if what is captured is blurry, they do not deal well with occlusions, and even issues like non-standard object poses, if the object is rotated in an unexpected way, that already causes issues for modern DNNs. And this is where multiple views of a scene can really help. To give you a sense why, we show this case of us capturing a specific object configuration in our lab. This is where we've placed a helmet on a laptop on a table, and we walked around it to capture different views of this arrangement. And then we sent those images to the very same DNN that identified objects in them. So you see that in the capture on the left, this DNN was able to identify both the helmet and the laptop. But in the capture on the right, it only got the helmet. So if we are able to make use of both of these captures, we should be able to improve the recognition for for the scenario on the right at the very least. And this is what we do in our work. We use the edge server to identify when images are corresponding to the different captures of the very same scene, to identify images that are spatially correlated. We also use the edge server to identify whether any of the images are corrupted by distortions. And we use the edge server to combine different inference results in the best possible way. Specifically for that, we use an approach that we termed auxiliary assisted multi-view ensemble learning, where we are combining outputs of different classifiers based on our projected confidence in their results. And we have demonstrated that this edge-supported approach improves recognition accuracy dramatically over what can be done with an AR device alone, especially in cases where AR device captures are corrupted by noise, such as motion blur, which is actually a very common scenario. I also want to talk about our work on using edge computing to improve depth sensing for AR devices. And this is directly related to the issue of a scale that I was showing before, that if you do not get depth right, we don't get scale right. And that's very noticeable to the users, and it's very commonly encountered in everyday world. So depth sensors are being incorporated into many high-end AR devices, including AR headsets. And they do help, but unfortunately, they have lots of artifacts in them. And you see some of the examples here on the screen. So in the image on the very left, looking at the RGB capture of the scene, we would expect depth measurements here to be fairly trivial. But if you look at the depth map, we see that large areas of it are actually missing. So for a very large number of pixels, the depth just isn't recorded. And this is a very common occurrence. We have seen this on headsets and mobile phones both. And it has to do with the properties of the type of sensing that's done to obtain depth data. That the sensor is generating infrared light that's sent in the environment, and it receives this data back. But then how well the received data looks depends on the surface that was encountered by the infrared beam. So if the surface is either too bright or too dark, or it's too far, or even if it's at an angle, then in many cases, depth data ends up being missing. And we've quantified this in our recent work, and the extent of such holes in depth data is quite dramatic in many modern devices. In many cases, there are not holes, but artifacts in depth data that are quite major as well. These examples are shown in the middle and to the right of the screen here. So in these cases, you would expect depth mapping to be fairly smooth and fairly high quality. But as we highlight in the blue squares here, something else is happening here, that the data just doesn't look right compared to what we see on RGB captures of these screens. And this also has to do with the properties of depth sensors, that in this case, this is associated with lens flare or reflections from the scene. What we can do to deal with these cases is develop a neural network that takes hints from both depth images and RGB images to correct holes and artifacts like these. But the issue is that these artifacts are fairly sizable. They cover a large area of the scene. And to be able to deal with such cases, the DNN that we built has to be necessarily complex and deep, since it needs to process large parts of the image at the same time. And this is where we to be able to do this in real time, we do need edge computing. Otherwise, there is just no chance that we would come close to meeting the associated latency budgets. So what we have done in our work is design a new deep neural network for addressing these holes and artifacts. And our neural network outperforms the state of the art and has been carefully engineered to reduce the computing latency dramatically, up to an order of magnitude over existing work. We've also built an edge-supported architecture that allows us to do this type of processing very, very quickly. The architecture is shown in the middle of the screen here. We take RGB and depth captures of AR devices. We send them wirelessly to the edge server, where they are pre-processed, aligned, and are passed through the DNN that we have designed. And then this in-painted depth map is sent back to the AR applications, where it is used to generate holograms that are of the right scale. And overall, end-to-end, this processing from the time that we capture the frames to the time that the frames can be used by the AR applications takes under 30 milliseconds, which essentially allows us to run them at the frame rate in many applications. And as I mentioned, our work outperforms the academic state of the art, existing DNNs. We have also compared it with the industry state of the art, that's Google Depth Lab APIs for working with depth maps on Android devices. And we have demonstrated that we significantly outperform Google Depth Lab on standard measures of error. And we have also demonstrated that this leads to important improvements in user experience with the system as well. So we show here, for instance, that our in holograms that are generated with our systems, their scale is perceived as being correct in many more cases than is the case with Depth Lab. So I'm very happy to share with you more details of this very recent work offline. And we have lots of other ongoing work on using IoT and edge computing to improve semantic and spatial awareness for mobile AR. I'm particularly excited about our work on using IoT and AR together to improve SLAM for AR devices, taking SLAM inputs from IoT devices and AR devices, relating SLAM performance to the state of the environment, and using IoT-based controls to change the state of the environment to optimize tracking for SLAM. And we have also been doing a lot of work on improving semantic awareness. What is known and what has often been observed is that traditional deep neural networks used for recognizing objects in the environment that are trained on existing large-scale data sets such as ImageNet. Unfortunately, they do not tend to do well in specific local conditions. So usually we need some amount of local data to fine-tune these classifiers to provide us with reliable awareness of objects in local conditions. And this is where applications of edge computing are very promising, that we can use edge computing to run advanced semantic awareness algorithms, and we can use it to guide the users to collect the right type of local data for ensuring that we are able to do fine-tuning in the right way for the local conditions. I'm very excited about this work. I think that this has the potential to make semantic awareness reliable in practical conditions for many exciting applications. I also want to talk briefly about how we can use multi-device architectures for improving user context awareness. And this is awareness of what the user is doing and how the user is feeling. Ideally, we would like AR experiences to be adapted to the state of the user. We would like to adapt the guidance to whether the user is concentrating on a task or whether they are tired, whether they're an expert in the task or whether they're a novice. So for instance, in our AR guided surgery applications, we would like to show different types of guidance to surgeons who are only training and to expert surgeons. And in all of work on user context awareness, the holy grail is not just detecting the states of the user, but also predicting them. And with that, we would be able to, for instance, know that the user is about to get tired. And then we can preemptively show them some augmentations that relax them or that get them to feel better before they start making mistakes on their important tasks. You need a lot of data for this, but this truly is a holy grail for user context awareness for AR as well as in other applications. And this is where there's a lot of potential for using wearables, IoT, and edge computing to make user context awareness algorithms reliable. IoT and wearables are naturally complementary with AR devices in this case. We are able to get different types of data about the user through these various channels. And being able to get this data and combine it will doubtlessly result in providing user context awareness that's much more reliable than what can be accomplished with AR devices alone. And in this case, edge computing is also important for multi-device coordination and for providing additional computational capabilities, as is the case for environmental awareness. But it also has many other uses. So for working with user context, privacy is important in many cases, and edge computing can offer additional ways of dealing with private data in a better way. So not sending sensitive user information to the cloud, but perhaps pre-processing it locally or making sure that the most sensitive information just does not leave the premises. And edge computing also has an important role in allowing us to train personalized algorithms for user context awareness. Unfortunately, what has been observed in a lot of work with user context awareness is that algorithms that are trained on general population do not do well on individuals unless we have some of that individual's data. So usually to make a lot of user context awareness algorithms reliable, we do need some data from the user. And this is, there are known algorithms for working with it, for fine-tuning deep neural networks, for techniques to reduce the amount of data that you need to get from the user. But ultimately, you do need to run training algorithms on user data. And this is where edge computing can be a tremendous asset, that you can do this kind of advanced computing, advanced machine learning training locally on computationally capable devices. I'll talk about our work on user context awareness with eye tracking. And eye tracking is a very important part of both augmented reality and virtual reality hardware already, and will be so in the future. In both AR and VR, eye tracking enables gaze-based interaction. That's important in many cases. It also enables the so-called foveated rendering. That's with eye tracking, we are able to generate sharp, high-quality content where the user is looking, and to reduce the quality of content where the user isn't looking. And this allows significant resource savings and will doubtlessly be important in the future as well. And eye tracking reveals an enormous amount of information about the user. We can tell if the user is expert or novice. We can tell if they're getting tired. And we can tell what they are doing, even if they are sitting still. So even if the user is just positioned somewhere and an accelerometer would not tell us much about what they're engaged in, their gaze patterns would actually be quite revealing. So some of the examples of human gaze patterns for different tasks are shown on the screen here. So for instance, this graph corresponds to someone reading text, and this one corresponds to someone watching a movie with subtitles. So you see that you kind of see where some of these gaze patterns come from. And you see that there ought to be a way of distinguishing these actions based on these eye patterns. And indeed, what we did in our work is to design a deep neural network that allows us to distinguish between these tasks. There has been work on gaze-based activity recognition before, but the performance of existing algorithms has been hampered by a wide variability of gaze signals between different users and between different eye trackers. We have designed a representation, a graph-based representation, that allowed us to get past that and to improve the reliability of user context detection dramatically. But in this case, similar to some of our other work, the DNN that we had to build for this case, since it required graph-based processing, it was too heavy to run on a mobile device. And this is where we used edge computing to get to the right latencies in this case. We designed, again, as I mentioned, we designed a DNN that significantly outperforms existing methods. We also designed it to perform very well in the so-called few-shot settings. So as I mentioned, we usually need some amount of user data for user context awareness. But in most cases, we cannot get huge amounts of this data. We can only ask user to do so much as part of the calibration. So in this case, this is called few-shot conditions, where we are only able to get limited amounts of data to train classifier on the specific user. And we have demonstrated that our system does significantly better in few-shot settings than all alternatives. We have designed edge support for it, where we take gaze points from an AR headset, and we worked with both Magic Leaps and HoloLenses. We send these gaze points to the edge server, where they are processed. We construct this gaze-based graph, and we run our deep neural network. And then we send the activity recognition result back to the AR headset, where it can be used to adapt the augmentation. So for instance, if we have identified that the user is enjoying a painting, we show them one augmentation. And if we have identified that they are reading text, we show them something else. And overall, with edge processing, we were able to get the overall latency of the system to under 100 milliseconds, which is very good for user-facing tasks, since this is the level of latency that ends up feeling just about instantaneous to the users. And we also fairly certain that we can get to better latencies if we spend more time optimizing the system for various communication elements. I also wanted to mention our other element of this work, and that is on generating data for training these eye movement-based classifiers. The challenge was creating classifiers that are based on gaze is that generally we need a fairly large data set of human actions to design the base classifier. And this can be problematic for small companies or startups in particular, as a significant investment into human data collection is required. What we have developed in our work is an alternative approach, where we are synthesizing gaze signals to train our classifiers. And our approach is based on the fundamentals of human visual processing. We have identified how exactly human visual processing works in several tasks, and we have designed software that emulates that to generate data that we can use to train classifiers. So I'll show you one example. This is how human visual attention works in a conversation. So an example of this is shown on the screen here. If we are talking to someone, our eyes move in a very particular way that we usually zoom in on the face of the person we are talking to. And when we zoom on their face, our attention alternates between their mouth, nose, and eyes areas. And this is biologically driven. That's very well known. It shows up in young children already. You look at the mouth of the speaker since you want additional hints for what you are hearing. And you look at their eyes and nose to get a sense of their attention and their emotions. So we have designed an algorithm that takes in video, such as this video of Anthony Fauci updating us on the state of the pandemic. It uses facial processing techniques to extract these areas that we know humans are focusing on. And it uses generative approaches to create data that very accurately corresponds to how a human would be alternating between these specific areas as they're having a conversation. And we are able to use this type of data to train our classifiers without human involvement whatsoever. I described the case of a conversation. Similar known gaze patterns exist for other tasks, such as scene processing or looking at a video or reading. And an example of those patterns is shown on the screen here. So we created an engine that we hope goes towards democratizing eye-based classifiers, since it does significantly reduce the extent of investment that's needed to start working with them. This work is about to appear at the conference in May, and I'm happy to share both the preprint as well as the software with those who are interested. So in summary, I talked about context awareness in this talk. Context awareness in terms of the awareness of the state of the environment and the state of the user as well. Awareness of the topology of the space around the AR device and the nature of objects and surfaces in the environment. And overall, while a lot of AR capabilities are already impressive, there is clearly more that needs to be done in these areas to make augmented reality truly reliable as it needs to be for many envisioned applications. And I described the approach to using multi-device architectures to overcome limitations of standalone AR, using IoT and wearables as additional sources of information, and potentially IoT as a way of controlling the environment as well to optimize AR performance. And edge computing for several of its capabilities, but especially for providing additional computing resources that allows us to run the type of algorithms that we cannot run on mobile AR devices, and allows us to make AR significantly more reliable in the future. There's of course a lot of future work to be done on all of this. We have recently outlined some of it in a workshop on building the foundations of the metaverse, and I'm happy to share the preprint as well. Overall, there's a lot of work that still needs to be done to be able to efficiently work with data that's captured by multiple devices. So for instance, the quality of the data that is captured by IoT devices and AR devices will vary depending on the circumstances. So for instance, the view of an AR device can be abstracted in one instance, and the view of the IoT device can be abstracted in another. So dealing with this requires new algorithms that us and other groups are working on. And on the side of user context awareness, it is particularly promising to use different types of modalities to sense user behavior and emotions at the same time. So simultaneously process user speech, eye patterns, and IoT videos, for instance. For this case, we need to create multimodal systems, multimodal deep neural networks, and there are some challenges that are associated with it that multiple groups are currently addressing as well. So my time is up. Our publications that you may be interested in are here. So these are our recent ones, and I'm happy to share with you some of the older ones as well. I would like to say special thanks to students and postdocs who have been pushing this vision forward over the last several years. They're showing on the left of the screen, and to a very large group of undergraduates who have been helping us out, some of whom are shown on the right of the screen. I would like to say thanks to our sponsors, and I'll take questions now. Thank you.
Fabulous. Thank you very, very much, Maria. That was an excellent, excellent talk. It didn't leave me with many questions. You connected the topics so smoothly together. It was very enjoyable to listen to and to learn. And when I invited you, I wasn't aware of all the range of topics and the different use cases that you have presented with, and the focus on optimization of the devices themselves. That's very interesting.
Thank you, Christian. Yeah, I think so when we met at AWE, I mainly talked about the environmental awareness side of the work, spatial and semantic awareness. But our work with users has been very interesting as well. There's clearly a lot of opportunities of adapting augmented reality to the state of the user, and there is a lot of work to be done on it, but the opportunities are endless as well.
That's right. That's right. And I think the condition and the status of an employee or a technician in the workplace is something that we envisaged being valuable, but have, at least in my opinion, been very, very it's hard to get that status. It's been very challenging to understand the physiology of the individual. As you said, each individual is very different, and so training for personalization and to detect the conditions of that users as they are changing is critical. And you also pointed out, I think very correctly, that that information, the users themselves don't feel that comfortable with the information leaving their own bodies, right?
Yeah, that's right.
And I feel like, well, where I'm looking, my gaze and my breathing patterns, that's my business. And what concern or interest or value could that be to, to my employer or to my manager somewhere? That's very, very delicate topics. And so, well,
Yeah, that's definitely true. So eye patterns especially, they are extremely revealing actually. So you can tell if, as I mentioned, you can tell if someone is a novice or an expert, since novices and experts really truly see the world in different ways. You can see, you can infer people's likes as well. You look at people you like in one way, and you look at people you don't like in other ways, or you just don't look at them at all. So there's some work that shows that eye patterns can reveal sexual preferences or racial biases. So it's very, very sensitive actually. So
it's
I'm
very,
very excited. Yeah, I'm very excited for using edge computing as an option for keeping this data local. So for never having it leave your premises for maybe adding additional noise to it before it goes to the cloud, or just not sharing it at all. And I think this opportunity for this more private training, more personalized training is huge in this space.
You don't usually think of the sensors as the eye detector as IoT devices. I didn't think of them that way, at least. I think of them as they're part of the headset itself. You spoke in the first part of your talk about scale errors and hologram scale errors. Can you talk about how often those are encountered, or how common these issues are relative to in your research?
Yes, so we actually studied this fairly carefully. So we ran a user study where we asked several AR users what spatial issues were commonly encountered by them. And scale errors came up as something that's very common for users of mobile phone AR in particular. That this is commonly encountered and this is commonly disruptive. And I've been actually discussing it in my class recently. I teach a class on edge computing where we talked about AR as a use case. And interestingly enough, my students who have all played with Pokemon Go, they immediately related to this point and said that in Pokemon Go, the scale issues in seeing Pokemon are very, very common. That it's common to see that it's common to see a Pokemon as either tiny or gigantic, and apparently it interferes with the gameplay. And out of my class, actually, a third of students have said that they have witnessed that.
Huh. That's interesting. Good. Maybe it's the difference between a mobile phone, a tablet, and a stereoscopic system like a HoloLens.
Yes,
Are
those
there
actually
any?
do tend to be better on HoloLens for sure. Yeah.
Yeah, I think that's probably the most common display. But in enterprise and industrial use cases so far, for stereoscopic, which is the only case when these holograms would be in the wrong place because that's stereo. Okay. Well, I'd like to thank you very much for this excellent talk. So many interesting topics, so many avenues for future research, and very stimulating. I hope that our community and specifically members of our committee, our research committee, will be able to follow up with you and pursue some of these avenues for future work. Thank you, Maria.
Thanks for having me, Christine.
Great, great, great. Appreciate it. Goodbye now.